And so now we'll move to our next talk, which is from David Heather from the European Space Agency. He's going to talk about the ESA Prospect payload for Luna 27, its status and the science activities that are going on. So David, over to you.
Thank you very much. Can you hear me okay?
Yes, we hear you.
Very good. I'm going to try this clicker thing as well to see if this works. Can you bring up the slides?
The slides are there. The slides are ready.
The slides are there. Okay, thank you. All right, thank you. So good afternoon or good day or whatever. Today I will give you a quick overview of the status of Prospect on the Luna 27 and some of the activities that they're following on the science side. Just a reminder, if I can change the slide. Excellent. So the clicker is working. Just a reminder, for those who don't know, Prospect is part of Luna 27, which itself is part of a suite of missions that the Russians are sending to the moon to investigate various things, such as volatiles and lunar resources. You'll notice that on Luna 25, there is Pilot D, a demonstrator of a precision landing package. That is well underway at the moment, the development and the preparations for that to fly. Prospect itself is going to be flying a couple of missions later on the Luna 27 mission. This is a static lander, and Prospect will be one of the major payload packages on that. We will also have Pilot, which is the full version of the demonstration in order to help target the landing and to do some dynamic appraisal of the landing before we get there to make sure that we can avoid hazards. So Prospect itself has rather a lot of objectives. I don't expect you to read through all of these. All I wanted to do here was to basically highlight the fact that we have very extended objectives, let's say, that pass beyond just looking for and analyzing the volatiles that we might find on the lunar surface. What I have done is highlight the objectives here which are particularly related to volatiles, which are, of course, of key importance. Something that you can read is a shorter version of the objectives. So here you can see basically what we're trying to do is to perform a cryogenic extraction of regolith from depths of 1 meter down to 1 meter. We will do this in order to characterize the polar surface and the subsurface environment, and of course to look for volatiles. We will try to determine the abundance of the volatiles, but also the composition and the origin of the volatiles. So this is quite ambitious, and in order to do this, we need quite a complicated and comprehensive package. We will also try to demonstrate some in situ extraction of oxygen from minerals, so do some ISRU experiments as well with Prospect. So this is what Prospect looks like, a bit of a schematic diagram, let's say an image of what Prospect looks like on Luna 27. On the left-hand side, you can see Proceed, which is the arm which contains the drill, which, as I said, will drill down to maximum depths of 1 meter. That drill arm itself can swing around, so we have access to various parts of the lunar surface, and we can select exactly where to drill. On the right-hand side, you can see that we have a sample inlet system, solid inlet system, excuse me, and the Prospect Analytical Laboratory. And the drill will basically drill down to the depth that we select. It will it will extract a sample. It will actually extract 2 samples, one small sample for the European payload and a larger sample that will go to the Russian payload. The arm will then swing around and deposit the samples through the solid inlet system, the smaller sample going to the European payload, where we have a carousel of ovens where we can do some stepped heating and pass the gases into the Prospect laboratory for analysis. And within the laboratory, we will have an ion trap mass spectrometer and a magnetic sector mass spectrometer to look for isotopes and composition and to try and give us a handle on the origin of the volatiles that we will hopefully find. To break that down a little bit into a simpler form, let's say, we can break Prospect into some various elements in the science that we'll be looking at. First, of course, is the drilling and geotechnics and sample handling, imaging, surface modeling, and spectral analysis. The sample analysis itself will be looking for noble gases, light elements, and isotopes using both the ion trap and the magnetic sector mass spectrometer. We'll also be looking at the thermal environment and looking at the volatile preservation in real life when we get to the moon. Of course, we're modeling that beforehand, which I will talk a little bit about shortly. And for the in situ resource utilization, we'll be doing some precursor experiments in prospecting. We also have a permittivity sensor, which is built into the drill. And that will be giving us some measurements approximately, I think it's 35 or 40 centimeters above the drill tip. So we'll be able to get some information about permittivity at those depths as well. Now, I don't have the facility to press play on this. Can somebody press play on the video if that's possible? Thank you very much. So this here is an animation of what we will basically be a standard operational sequence, let's say, for Prospect. What you can see here, well, it's very small for me, is the Prospect system, basically. We will first of all do some imaging of the surface. You'll see the LEDs lighting up and imaging the surface. So we have LED illumination built into the drill system. We'll analyze the surface before the drill is deployed. So we will then deploy the drill and drill down to the selected depth. Once we've reached those depths, you'll see that the site is illuminated again, and we will be looking at what we call the cuttings pile, so the debris which is left at the top of the drill. So we can start to analyze grain size, a little bit about composition, because we will have multispectral analyses. We will then extract the drill, and the drill arm will swing around to deposit the sample into the solid inlet system. And here you're not going to be able to see very much, but we will also be doing some more imaging of the sample itself as it's deposited into the carousel, where it's sealed into the ovens, and we will do the analyses with the spectrometers. And I think this sequence ends with the drill being deployed again to take a second measurement. But that's basically the operational sequence. And here we actually see the drill going back into the same hole, although of course we will have we will have the possibility to drill multiple boreholes. I hope that was clear. It was quite difficult for me to see the animation. So the next slide seems to have disappeared. Are the slides still up? Yeah, okay. Okay, so I'll just highlight now a few activities that are ongoing with the science team. We are, of course, working on many things to try to prepare for this mission. We're looking at the thermal modeling throughout the entire chain of drilling and sampling and analyses. So we need to really understand the thermal environment there in order to make sure that we can keep the volatiles that are in the sample as much as possible. We have to understand the thermal radiative environment, which is produced by the complex lunar polar illumination conditions. You can see an image on the right-hand side of an analysis there done by some of the science team and the comparisons that we're doing with some known thermal models. We also have to try to understand the fractionation behavior of D over H, so with sublimation. This is not very well known at the moment, but needs to be well characterized so that we can make sure that we understand the uncertainties when we start to take the measurements on the lunar surface. Some further activities, as I've mentioned, volatile preservation is key. You'll see on the right-hand side a kind of a schematic to show the trend of what we're seeing in terms of modeling the volatile preservation throughout the entire chain of operations. We have a requirement where we need to keep or we can afford to lose at most 35% of the volatiles from the point of sample, of obtaining the sample and the point of measuring and analysing the sample itself. We're also in the process at the moment of looking at the camera system and looking at the dust sensitivity in the camera system, assessing the magnitude and impact of all of the vectors which could have an impact on contamination throughout the entire chain of measurements as well. And we're looking at the prioritization of some potential operational sequences, making sure that we can try and squeeze in as much as possible in the first few operations to make sure that we can get the science back that we need, and several other key areas, of course. Okay, thank you very much. Thanks. So this is one thing that was completed by the science team last week. We did a demonstration of oxygen extraction using by Prosper, basically using the ground system here. Of course, the extraction of water and oxygen from lunar regolith using hydrogen reduction normally requires a constant flow of hydrogen, which we cannot do with Prosper. So what we've tried to do with this ground setup is to demonstrate that this will actually be possible on the moon, because we were concerned that the reaction might be suppressed. And with this experiment, it showed that we could, in fact, or we should in fact be able to do this without any issues. So the ISIU aspects of the experiment should work perfectly well. The results of this also showed that there was a clear correspondence between the ilmenite content of a sample and the resulting yield of oxygen. So ilmenite will be a key marker for our ISIU studies. Final thing that we're looking at, of course, is the landing site evaluation. So there's an awful lot of work that we have to do to try to better understand the illumination, the complex illumination and thermal conditions that we're going to experience when we get to the moon. Here you can see an analysis that we're doing on the 8 prospective landing sites to try to understand what we might experience when we get there. This will, of course, have a key impact on the volatile preservation activities as well. So this is work in progress. There's all sorts of elements that we have to try and weave into this study. And since I'm running out of time, I will not talk much more about it. And I think I will finish there. So thank you very much.
That's great. Thank you very much, Dave. So a couple of questions for you. The first was related to the location. I'll paraphrase the question a little bit. In the images and the fact you have solar panels, this mission is not going to land in a permanently shaded region, but somewhere else. So how does that correspond to the search for volatiles? How do you expect to find volatiles in these locations?
This is exactly why we're doing the analysis that I mentioned in the final slide. It's extremely complex. The needs that we have in terms of power and survival have to be somehow matched with the needs in terms of hoping to find volatiles. Subsurface volatiles, we should still be able to find them at depths of more than 30 centimeters, we hope, even in areas which have partial illumination. So what we're trying to do with this landing site analysis is try and balance all of those different issues and try to work with our Russian partners to find the best places where we can both survive and find volatiles.
And just to say, is it also true that the system goes to much higher temperatures for those hydrogen reduction processes? So you'd also be able to do science and resources investigations that are a higher temperature. And so even if there are no volatiles there, you still get to deliver some science.
Exactly. We still do ISIU. Yes, we still get that.
And then there was one other question on the heat generation from the drill. And the fact that that's also going to create some issues for volatile preservation, and you talked a little bit about that with some of the modelling you're doing. But what's the approach to mitigating that drill heating?
The latest modelling has shown that it could potentially be quite a big issue in terms of volatile loss if we simply drill, extract, and remove the drill and do the sample straight away. What we've actually found, the best option for us is if we drill and extract the sample, if we then pause for approximately 400 seconds, then the system is allowed to cool down to a level where volatiles are not lost. and we can preserve much more of the volatiles in the final sample. So at the moment, this is basically the approach that we're looking at. We're still in the process of modeling a lot of this, so it's early days, but at the moment it looks like a pause after sample extraction is the best option for us to preserve the volatiles.
That's great. Thank you very much, Dave. Thank you for all the questions.